The third major field that underwent a revolution in the late 19th and early 20th centuries was physics, and its great transformative figure was the German scientist Albert Einstein. To appreciate his contributions, we must first understand what physics looked like around the year 1900. For more than 2 centuries, the study of physics rested firmly on the ideas of Isaac Newton, whose laws appeared to explain the workings of the universe with remarkable success. Newtonian physics held that all physical phenomena result from interactions between matter and energy operating within a framework of absolute space and absolute time. According to this view, space and time existed independently and uniformly throughout the universe, providing a fixed stage on which all physical events occurred. Newton also maintained that matter could neither be created nor destroyed, and that energy was likewise conserved, existing as a separate and unchanging quantity. Together, these principles described a universe that seemed orderly, predictable, and governed by rational laws that educated individuals could understand through observation and mathematics. By the late 19th century, however, a growing number of scientific discoveries began to expose weaknesses in this framework, suggesting that the Newtonian universe was not as complete or as certain as once believed. These emerging contradictions would ultimately pave the way for a revolution in physics led by Albert Einstein. One of the major challenges facing 19th century physics came from the study of radioactivity. Through her pioneering experiments with the element radium, Marie Curie discovered that certain substances spontaneously emitted powerful forms of radiation. Even more surprising, careful measurements suggested that radium appeared to lose a small amount of mass as it released energy. This finding raised profound questions about the nature of matter and energy, because it seemed to contradict the Newtonian view that matter and energy were separate entities that were independently conserved. If matter could gradually disappear while energy was produced, then something fundamental about the structure of the universe was not yet understood. These puzzling observations suggested that matter might be transforming into energy, a possibility that traditional physics could not explain. The mystery of radioactivity became one of several scientific problems that exposed the limitations of the Newtonian worldview and paved the way for Einstein's revolutionary insights into the relationship between matter and energy. Experiments in the late 19th and early 20th centuries revealed a major problem in physics. Light did not behave the way scientists expected. Some experiments demonstrated that light acted like a wave, spreading out and producing interference patterns much like ripples on water. Other experiments suggested that light behaved as if it were made up of tiny particles, later called photons. This apparent contradiction puzzled physicists because classical science assumed that light should have only one fundamental nature. Even more troubling were the findings of researchers such as Albert Michelson, who attempted to measure the Earth's motion through space by observing the behavior of light. According to Newtonian physics, the speed of light should vary depending on the motion of the observer, much as the speed of a thrown ball changes relative to someone moving toward or away from it. Instead, experiments consistently showed that light always traveled at the same speed regardless of the direction of measurement or the motion of the observer. This unexpected result conflicted with the assumptions of classical physics and suggested that long-accepted ideas about space, time, and motion were incomplete. The evidence increasingly pointed to a fundamental problem within the Newtonian model of the universe, setting the stage for Einstein's revolutionary theory of relativity, which would provide a new explanation for these puzzling observations. In 1905, Albert Einstein published a groundbreaking paper that introduced the special theory of relativity, offering a radically new way of understanding the universe. For centuries, scientists had accepted Isaac Newton's view that space and time were separate, absolute entities that remained constant throughout the universe. Einstein challenged this assumption by arguing that space and time are actually interconnected and form a single four-dimensional structure known as the space-time continuum. According to his theory, measurements of space and time are not fixed, but depend upon the observer's motion. As an object moves faster, especially at speeds approaching the speed of light, time slows down relative to a stationary observer, a phenomenon known as time dilation. At the same time, the length of objects in the direction of motion appears to contract, a phenomenon called length contraction. Einstein's theory also implied that if an object could reach the speed of light, approximately 186,000 miles per second, time would effectively stop for that object. These ideas were astonishing because they contradicted everyday experience and overturned the long-standing Newtonian picture of a universe governed by fixed, absolute laws of space and time. Relativity transformed modern physics and fundamentally changed humanity's understanding of reality. Einstein also proposed one of the most famous equations in the history of science, E equals mc². This equation demonstrated that matter and energy are not separate entities, but are instead different forms of the same underlying reality. According to the equation, even a tiny amount of matter can be converted into an enormous amount of energy, because the speed of light squared is an extremely large number. This insight helped explain phenomena that had puzzled scientists, including the work of Marie Curie and other researchers studying radioactivity. The small amount of mass that appeared to disappear during radioactive decay was not actually lost. It was being transformed into energy. Einstein's discovery revealed a fundamental connection between matter and energy and revolutionized the understanding of the physical world. In the decades that followed, this principle became the scientific foundation for nuclear power and nuclear weapons, demonstrating both the immense potential and the profound consequences of modern physics. Einstein did not stop with his special theory of relativity. In 1915 and 1916, he introduced the General Theory of Relativity, a revolutionary new explanation of gravity that fundamentally changed the way scientists understood the universe. Rather than viewing gravity as an invisible force that pulls objects toward one another, as Isaac Newton had proposed, Einstein argued that gravity results from the curvature of space-time itself. According to this theory, massive objects such as planets, stars, and galaxies distort the fabric of space-time around them, much as a heavy object placed on a stretched sheet causes it to bend. Smaller objects then move along these curves, creating the effect that we perceive as gravitational attraction. General relativity successfully explained several astronomical phenomena that Newton's laws could not fully account for, including irregularities in the orbit of Mercury and the bending of light by gravity. Einstein's theory transformed modern physics, providing a new framework for understanding the cosmos and laying the foundation for many later discoveries in astronomy and cosmology. In its impact on science, general relativity was as revolutionary as Darwin's theory of evolution was for biology, and Freud's theories of the unconscious were for psychology, fundamentally reshaping humanity's understanding of the world and its place within it. Einstein's theories were disturbing to many people because they challenged humanity's understanding of reality itself. Unlike Newton's laws of motion and gravity, which an educated person could grasp through observation and common sense, Einstein's theories of relativity relied on advanced mathematics, abstract concepts, and conclusions that often seemed to contradict everyday experience. Ideas such as time slowing down, space being curved, and measurements depending on the observer's frame of reference were difficult for the general public to understand. As Einstein's work gained attention, many people concluded, sometimes incorrectly, that relativity meant there were no absolute truths and that reality itself had become relative. While Einstein was speaking about the physical universe rather than morality or philosophy, his theories contributed to a growing sense that the world was far more complex, uncertain, and mysterious than previous generations had believed. In this way, Einstein joined Darwin and Freud as one of the great thinkers whose ideas transformed modern understanding and challenged long-established assumptions about humanity and the universe. The intellectual and scientific revolutions of the early 20th century extended beyond science and psychology and profoundly influenced culture and the arts. Einstein's theories of relativity challenged traditional assumptions about space, time, and the nature of reality, contributing to a broader climate in which established ways of understanding the world were increasingly questioned. As reality came to be viewed as more complex, fluid, and subjective than previously believed, many artists began to reject traditional forms of realism. Instead of attempting to reproduce the visible world with accuracy, they sought to explore perception, emotion, perspective, and the hidden dimensions of human experience. This shift helped fuel the growth of abstract art, in which paintings often abandoned recognizable subjects altogether in favor of shapes, colors, and forms designed to express deeper ideas or feelings. Although Einstein did not create abstract art or directly instruct artists on how to paint, his revolutionary ideas became part of a larger cultural movement that encouraged people to rethink long-held assumptions and explore new ways of understanding reality. The early 20th century witnessed a series of intellectual revolutions that challenged many of the assumptions on which Western civilization had long relied. Charles Darwin's theory of evolution suggested that humans were the product of a natural process driven by competition and adaptation, rather than a uniquely privileged creation. Sigmund Freud argued that people are not fully rational beings who understand themselves, but are instead heavily influenced by unconscious desires, fears, and instincts. Albert Einstein's work on relativity overturned traditional understandings of space, time, and the physical universe, demonstrating that reality was far more complex than previously believed. Together, these thinkers undermined confidence in long-standing ideas about certainty, progress, and humanity's special place in the world. For many people, these new theories were unsettling because they seemed to erode faith in reason, stability, and human control. Einstein suggested that the universe could not be understood through simple, absolute laws. Freud claimed that individuals could not fully know or control the forces operating within their own minds. Darwin portrayed nature as a relentless struggle for survival rather than a harmonious and purposeful system. Although these ideas gradually gained influence, their broader cultural impact became especially significant after World War I. The unprecedented destruction of the war, with its trench warfare, mass casualties, advanced weaponry, and political upheaval, shattered many people's belief that modern civilization was steadily progressing toward greater order, morality, and rationality. In the aftermath, the old confidence in reason and stability seemed deeply damaged, leading many to view the 20th century as an era of uncertainty, anxiety, and profound change.